Geography here at Appalachian State. It's great to see this turnout. I want to recognize a few people. First of all, we've got a team from the University of Maine here, including Dr. Paul Mayewski, who you'll hear more about in just a minute. I want to acknowledge Sean Burkle. Sean, he's a faculty member at the University of Maine. Charles Rada, graduate student. We've got Heather Clifford, graduate student, and Mario, where are you? Oh yeah, Mario back there. So welcome. We've had meetings the last day and a half here, and it's been great to have you all on our campus. I also want to introduce Dr. Anton Simon. He's a research professor at Appalachian State, though he's not here on campus that often. He's based out of New York. He's an important collaborator and colleague, and I've asked him to introduce our main guest this afternoon. So Anton, I'll turn it over to you.
Thank you, Baker, and hello everyone. Great to see lots of familiar faces and friends here. And I've also a 51-page cheat sheet, known as Dr. Mayewski's CV. Not exaggerating. It's an extraordinary pleasure to introduce my friend and colleague, now Dr. Mayewski. We've been collaborating the past couple of years on a major National Science Foundation project. Classic collaboration. Appalachian State handles one sphere of work in the tropical Andes, and Paul's team handles another. I'm sure you'll get to hear much more about that at some point. Dr. Mayewski has, as you can imagine, a rather extraordinary breadth of experience. One of the things I'm most interested in is when you hear all these accomplishments. It's a product of the public school system in New York City. I don't think that should be trivialized. I think public schools have amazing resources. And he and some of his classmates from that school include some very famous people who went to Princeton High School in the Bronx. I think are living testimony to that legacy, which is great. Then went to the State University of New York at Buffalo, to a bachelor's degree in geological sciences, followed by a PhD at Ohio State, and that was the Institute of Polar Studies. And so that began all on his trajectory, working in the polar regions, and there's very, very few people in the world that spend quite as much time in hard, difficult places as Paul has, gathering data, probably having a lot of fun at the same time as well. This includes the third pole, the high Himalayas, where he's led expeditions to Mount Everest. What's your expedition count now? 55? He's led 55 major expeditions over several decades now to incredible places. It's like a living National Geographic magazine when you're looking through this CV. Quite extraordinary, and you won't surprise you to know that Paul is 350 years old. So this period of time. So I'll just a very brief introduction to our project partnerships. About those of you who know Dr. Perry know about his long-standing interest in the Andes, and he takes student groups down every year as part of the study abroad program here. Wonderful experience. A show of hands who's been down there before? Quite a few, that's terrific. All right. So yeah, lots of people end up getting graduate degrees following those trips they get very excited about. It's a wonderful place to work. We've been working studying the precipitation dynamics of this area and the meteorology of the region. Paul's interest is long-term paleoclimate ice cores. So our partnership basically links the studies of present-day climatology and meteorology, and then trying to better understand what we can derive from ice cores. And I think ice cores is probably the focus of what you speak of today for the most part. That's enough from me, Paul. It's truly a pleasure to welcome you. Thank you.
Well, thank you so much, Anton. Anton has a very impressive record himself. One day I had the opportunity to introduce him. Actually, didn't quite start in New York City. I started in Scotland and then moved to England, but eventually came to this country and have been here ever since. This is an unbelievable campus that you have here. So impressed. It's a beautiful location, beautiful buildings, but what's way more impressive than the campus are the faculty and students that you have here. It's really a great pleasure to be at Appalachian State, to work with Baker, Anton, and all of the students. You have a lot to be proud of, and we're really privileged to be able to work with this team because they, as you'll find out, the sort of things that we don't study, they do, and it's really the perfect match. So let me take you through sort of perhaps a rather different sort of presentation. It's a very personal presentation because I'm 350 years old. I have a great deal of experience, and I thought it would be interesting for you to see from one climate scientist, from actually a glaciologist's point of view, how the field has progressed. And I give it to you in a very personal way because that's the way I understand it. So it's going to be a mixture, as you can see, of exploration, adventure, and then some what I hope you will agree with are some important realizations about how the climate system operates. But it's a mixture back and forth of all of these things. So early on, when I was at university, I was extremely excited about going to the Antarctic. And as soon as I graduated from university, because I'd already been hooked up with a professor who'd been there, I got to go to the Antarctic. And I didn't actually take this. I didn't take this picture from the air. I took it from another aircraft. That's a C-130. When I first went down to Antarctica, C-130s were almost too modern for us. We used other aircraft. But it is an absolutely remarkable place. To give you a slightly better feeling for what it looks like, it says the early years. Those are my early years, not the early years of the Antarctic. Mount Erebus off in the distance is 15,000 feet high. This is a floating mass of ice called the Ross Ice Shelf. If you track it back inland, it's the size of Texas. If you look at these icebergs, each one is the size of a city block. They're icebergs that come off Antarctica that are the size of small states. And if you look at the ice edge here, it sticks out of the water about 400 feet. And obviously, there's a lot more ice below that. So this is a vast, vast continent. It's 1.5 times the size of the United States. The average ice thickness is 6,000 feet. And the population, certainly when I went there originally, was probably on the order of about 500 to 1,000 people on a temporary basis, and they're particularly spread out in stations. Understanding scale in this particular part of the world is almost impossible. You think that that mountain is 2 miles away, then you realize it's 15,000 feet. If it's 50 miles away, everything is very, very hard to understand scale-wise. Now, this is me when I was about your age. And when I went to the Antarctic, obviously darker hair, more hair than I have now. When I went to the Antarctic the first time, I was really absolutely bowled over, very proud of myself. And we understood the Antarctic to be an absolutely timeless place. NASA sent astronauts to Antarctica because it was about as close as you could get, they thought, to Mars. Everything absolutely stagnant. The reason we thought it was stagnant was because rocks like this, remember there's no water that's moving around, average temperatures in the interior are about -50 to -60 degrees centigrade, and rocks like this could be determined geochemically at that time to have taken about 2 million years to get carved this way. So for this rock to sit here for 2 million years and have this shape clearly demonstrates that this continent is completely unchanged. And therefore, at least at that time, we thought has absolutely zero relevance to anything else that goes on in the rest of the world. The other thing that convinced scientists in general that this was an unchanging place was the finding of these juvenile seals along the coast of Antarctica. And these juvenile seals, when you go up to them, obviously he's wind sculpture, the bones are showing. When you flip them over, you touch the fur, and it's as if you were touching a live seal from that period. Radiocarbon dating suggests that this seal is on the order of 6,000 years old. So for this seal to sit here, or lie here for 6,000 years, become abraded, clearly this is a place where nothing ever changes. Well, after a certain amount of time in the mountains, I started running expeditions into unexplored parts of Antarctica. There was barely any air photography. Most of it just looked white, obviously. There are a few mountains sticking up, and these mountains stick up because they're higher than the 6,000-foot average surface in the area. So we started going back and forth through these mountain ranges out onto the plateau. We noticed something very interesting. These small glaciers that form in the mountains as they make their way off the mountains, they don't necessarily come right onto the ice sheet, but we realized that they had actually changed their shape in what we thought was the recent past, and the recent past for us would have been the last few hundred years. So it was the first indication that maybe things do change, but they change slowly. These glaciers were retreating a little bit. So as time went on, maybe fourth and fifth expedition, we started to drill ice cores into these places, and we would carry these actually a lighter version of this drill rig with us, typically 4 people, 2 snowmobiles, 4 sleds, unsupported for 120 days at a time, traveling across the ice sheet. There wasn't a GPS that we could use. You had to use a sextant, and most of the time you couldn't use that because the weather was so bad. So we would put out stakes, basically like dropping the little pieces of sugar along the way, which wouldn't work well in Antarctica. And then on the way back, you pick them up. If you had a mountain range, it was easy enough to tell where we were going. So this was very, very early exploration. And these ice cores, as it turns out, have become very valuable. When we first started doing them, we didn't really have a clue what we would get from them. We were not the first by any means to do this. But as it's turned out, you can interpret past temperature, precipitation, atmospheric circulation, sea ice extent, volcanic activity, solar activity, forest fire burning, pollutants from or human activity, biological activity in the ocean, biological activity on land, and it just goes on and on and on. These turn out to be a remarkable archive. And when we first started studying them, you could maybe tell decade by decade how things have changed. Now we're going back into the 1 to 2 million year era, certainly starting from the top. And nowadays we can actually look storm by storm going back long periods of time. So I spent years in the Antarctic, and I have continued since then, but I started to think this is such a remote place, it couldn't possibly have anything to do with humans. And after spending a lot of months in the Antarctic, I decided it would be nice to be closer to some people for a little while. So if you want to go to a place that has glaciers and has a lot of people, you go to the Himalayas. And this is India. And I thought that if we went and applied some of the methodologies that we've been using in the Antarctic, we might be able to solve some problems that would be of interest to people. Because remember, Antarctica is so far away from everybody that it couldn't possibly have any relevance to the rest of the world. So I wanted to find a place that other people had gone to that might have the right conditions. Very few people had worked in this area, but I did come across a book written by Fanny Bullock Workman, and she was a famous climber in the early 1900s. There she is. She did all of her climbing in this dress. And Nun Kun turns out to be one of the places she went. It's in Ladakh, right on the border with Pakistan, and we decided that we would go there. We made our way from, at that time I was at the University of New Hampshire, eventually to the top of this plateau where we went to work, which I'll take you to in a moment. It took us about 6 weeks to make the trek. By the time we got into the valley that was leading to this place, we encountered the first part of the valley primarily has Muslims in it, and then as you go farther north, primarily Buddhists. And we encountered these people with Muslim. They tend to be separated from the rest of the world for about 9 months a year. They're actually sitting on top of their house. Very, very isolated people. The average lifespan for men was about 35 to 40 years old. And the average lifespan for women was about 23. Probably still is, about 23 years. Very, very harsh environment. And I managed to collect a group of the local men. Turned out to be eventually about 40 of them porters. Some of them had actually come over from the war between Afghanistan and the Soviet Union. They escaped across Pakistan and Afghanistan, settled in this area, and I assumed that they would know exactly how to take me to the place in the mountains that I wanted to go, which of course is pretty stupid. People who are spending all of their time trying to survive don't go into high elevation. So we spent a couple of weeks just trying to find the route. We weren't allowed to have maps in this area. We weren't allowed to have any sort of communication, and the satellite imagery didn't show anything except clouds. So we gradually made our way, as I said, taking another couple of weeks, eventually up to 20,000 feet. These are a group of the porters. We went up over 3 ice falls, 1, 2, and 3, and these ice falls are each about 500 feet high, having to go up and down on a regular basis. staying away from these slopes during the warm time of the day when avalanches tend to cover them. In fact, on the way up, we had to put up a camp that was away from the ice, not just because of the avalanches, but because the air temperatures were well over 100 degrees Fahrenheit, and you could barely move around. So we'd spend a couple of hours in the tents and then continue to carry loads all the way up. So on the way up to the plateau, which is right up there, about 20,000 feet, we encountered something in a crevasse that we had hoped we would find. It turned out to be these layers. And these layers are dust events that come off the Tibetan Plateau to the north, and those dust events come in from early in the springtime, and this makes this effectively a giant tree ring, in which you can count back year by year, which is very, very important for an ice core, because we want to be able to relate it to the modern, calibrate it to the modern record, and go back in time. So we collected an ice core. We were primarily interested in understanding something about the Indian monsoon. During the summer, the Indian monsoon brings moisture up into the Himalayas, and it's stored up there, and then, of course, as it's warmer, it comes back down, as water has a lot to do with agriculture throughout the Indo-Gangetic Plain. And we were semi-successful in that. It's still a problem that's not entirely understood. But a very interesting thing happened. And this thing actually was a turning point in my entire career. We spent several weeks up at about 20,000 feet, and there was a snowstorm, and it turns out that we could see snow coming from the Tibetan Plateau, which is from the north, high and cold and dusty. And we could see air masses, precipitating snow, coming from the Indian Plains. Very low, marine air masses, very wet, a lot of agricultural products and chemistry ideally mixed up in that air. And it occurred to us that maybe we could put a chemical label on these air masses. Because if you could go back through time and understand when the air masses were coming from the north, when they were coming from the south, you could actually reconstruct back through time the history of this Indian monsoon. And we were able to do that. Today, we can, of course, do this much more easily using things like this NASA imagery. This is actually real-time video loop of how atmospheric circulation is making its way around the planet. And what they've done is they've colorized these air masses. This is now 35 years after we did this work, and these air masses are colorized. In this case, this is sea salt, that color. This one up here, the light white color, are air masses that are charged with an awful lot of sulfur and nitrogen from human emissions. This one is quite remarkable. These are dusts that are coming off the Sahara, and notice that those dusts make their way all into Central America and North and South America, and the green are air masses that are coming off regions with a tremendous amount of biomass burning. So, back 35 years prior to this, we didn't have this ability, but we were able to show that within the chemistry of these air masses, we could see chemical signatures that told us which way the air masses were, where they had come from primarily. So why is that important? Why do you want to chemically fingerprint an air mass? One of the reasons is that you can tell the source of that air mass. Let's say it comes off the Sahara, has a certain type of chemistry. The other is that you can tell differences in the emissions from that particular region. Now, the emissions might be related to increased aridification of the desert. They might be related to increased levels of sulfur, related, for example, to acid rain. They can tell you a whole variety of things. So there's a whole range of reasons for understanding changes in emission strength of chemistry transported by air masses, but perhaps the most important thing is the fact that the primary reason why we have warm temperatures, particularly yesterday here, and why you'll have cool temperatures a few days from now, has to do with the direction that the wind is blowing, where it's coming from, whether it brings in, and how much heat it brings in, moisture, and pollution. So if you understand where air masses go, you have gone a long way in understanding how the weather operates and how climate operates. In addition, whenever cold and warm air masses come together, you can have very extreme events, extreme storms. So this was a lead up to potentially understanding more about storms. So the next thing we did was to approach the Environmental Protection Agency, and this was a period in the 1980s during which, of course, the big environmental issue was acid rain, sulfur and nitrogen in the atmosphere. The big debate was whether or not humans had actually increased the levels of acid rain, and we made the case that by drilling back through time, and we went back about 300 years, we could go to the pre-industrial era, and sure enough, we found a dramatic increase in the baseline levels of sulfur and nitrogen in the atmosphere, beginning in the early 1900s for sulfur, and then about 1930, actually 1940s in particular for nitrogen, because it's largely emitted by automobiles. So this had relevance in providing perspective about how much of an impact humans had on the chemistry of the atmosphere, and it also turned out that in our record, we could see not only the rise of levels of sulfur in the atmosphere, but we could also see it flattening out and beginning to go back down again, and this was a consequence of clean air legislation, which is very important, demonstrating that in fact, with the right sort of legislation, you can clean up air masses. So, where would you go next if you wanted to find out, for example, what would the most natural levels of a particular chemistry look like on the planet? So you go to the most remote part of the world, interior of Antarctica, that ought to be the cleanest place in the world. And what the levels that you find there should be significantly lower than the rest of the planet because it's so distant from so many things. So this particular one was a sledge pull and traverse that we did out in the region of South Pole. Mean annual temperature here is about minus 52 degrees centigrade, and in order to do chemical sampling the way we do, you pull the sled out or snowmobile out, you get to a certain point, you get out, you ski farther, upwind, because you want to get away from any pollutant levels, because the expectation is that the pollutant levels that you're going to find will be very, very low, and then you don a clean suit because you haven't washed in the last 120 days. You put a mask over your face. Fortunately, you don't smell yourself because it's so cold. And then you, with clean hands, you pick up some snow. And we found some fascinating things. We did the same thing across Greenland a few years later. And without going into a lot of detail, what we found was the following. This is a record that goes back from today, 5,000 years ago. And you can see in all, this particular one here is population. That one we don't get from ice cores, but everything else we get from ice cores. And if you look carefully, you'll see boxed in for the last 150 years. In particular, in the last 150 years, you see a dramatic rise in all of these things. Most obviously, CO2, nitrous oxide, methane, radioactivity emitted by bomb activity, nuclear accidents, sulfur in the atmosphere, nitrogen in the atmosphere, copper, lead, mercury, and here are all of the primary categories, engineered chemicals, and a variety of other things. These are anomalously high in the last 5,000 years, and I could easily make the statement that if you go back to the beginning of Earth history, certainly some of these things have been high in the past, but this combination of increased levels is absolutely unsurpassed in Earth history. So we live in a very different time than any of our ancestors lived, a time in which the air masses are significantly more charged with pollutants, with natural chemistry, a variety of things. As we've continued our work, even into Antarctica, and notice here Mario Potocki in the back of the room, this is his work. We've actually found, for example, that in the last 100 years, uranium, which we can track to Australia, open pit mining, levels of uranium on the edge of the Antarctic Peninsula are about 10 to 20 to 50 times higher in the last 35 years. And levels of copper, arsenic, and lead, in particular coming off South America. Copper is a big deal, particularly in Chile. From open pit mining, those levels have increased throughout the Antarctic to very significantly higher, 10 times higher, if not 100 times higher. So even the surface of Antarctica today is impacted by human activity. One of the other studies that we've done, now that we have significantly more detailed records, this one goes from today, roughly the year 2000, back to basically 2,000 years ago. In this particular case, we're in the Swiss Alps. We're taking a look at levels of lead going back through time. Lead, as you know, is not good neurologically for humans or ecosystems. And all of a sudden, when we examined this lead, we found out that between 1349 and 1353, the levels of lead, and this is work that Heather Clifford in the back of the room worked on, the levels go almost to zero. Now, why is that important, and how did those levels go to zero when, in fact, this is a log scale, when, in fact, they were close to 100 in this particular case, very small units, parts per quadrillion. Well, it turns out that this one very anomalous event, the Black Death, is a time when about 50% of the population of Europe died from the Black Death. So they stopped smelting metals, they stopped mining metals, and literally the levels went to zero. There are other times when it went pretty low, but as it turns out, this one in particular and this one are directly related to a pandemic, when people were no longer able to continue life the way they normally did. But what's even more important today is that what is considered to be a safe level of the atmosphere in Europe is closer to this, because that was assumed to be the natural level. But in fact, whenever you find a lower level that's explainable, that's the true natural level. So even what's considered to be safe in Europe, which is very strict air quality, probably 10 times higher than what is naturally in the atmosphere. So why do we care so much about air chemistry? Because 7 million people a year die prematurely from bad air quality, and that is approximately 1 in 10 deaths. 10% of all deaths are related in one way or another to air quality. Why? I like to call it the toxic climate cocktail. Because many of these chemicals end up clogging up your lungs. They create neurological problems, cancers. And then as you begin to look at the other effects of increased levels of greenhouse gases, warming leads to vector-borne diseases. In Maine, we've only gotten Lyme tick in the last 5 years. The last 10 years. Before that, there was no Lyme tick. Drought, ecosystem upheaval because of ocean acidification. So what we've done to the atmosphere has been very significant in terms of health. That's the bad story. The other part of the bad story, of course, is that as you add greenhouse gases to the atmosphere, these things stay in the atmosphere. They distribute themselves because they're gases. They distribute globally around the planet, and they can last for centuries before they get re-involved in the carbon cycle. These super nasty things, lead, cadmium, particulates, acid rain, they don't warm, but they can, in fact, in some cases, like particulates, they can actually shield incoming radiation. They can offset warming through cooling, but they have, and they're nasty, but they have a very local to regional range, and they can drop out of the atmosphere very, very fast. The classic example, unfortunately, is 9/11. When the aircraft was shut down over the United States during 9/11, it was, for a few days, it was the cleanest that air existed over the United States for many, many years. So this is good news, that you can actually clean the atmosphere up quite quickly if you have the right conditions. So we became very interested in what's the distribution of air quality around the United States. The EPA does a phenomenal job of collecting air quality data, and we put together a synthesis of they don't do such a great job of necessarily advertising and showing you how to do it. So we took their remarkable data, put it together in what's called 10 green, and this single number tells you how clean your air quality is. Orono is about a 5. Nobody gets any better than an 8, because 2 of the pollutant measures, these are the 10 primary pollutants identified by EPA, because one of them is carbon dioxide, the other are greenhouse gases, and they're high all over the world. Green is good, it means they're in the safe range. Red is not good, and gray means that there is no measurement. And if you compare Orono to, it's way better to live in Orono than Los Angeles. Los Angeles is a 3. So I hope you're asking yourself, what is Boone? And Boone is a 6. Nobody gets good gas levels, but you have high of one particular type of heavy metal, and you have relatively high levels of small particulates. These are the things that are so small that they get into the alveoli in your lungs, and they don't come back out again. So let's look in a little bit more detail, and you can get this on any any computer platform that you want, including your smartphone. And this is the reason that the levels are unhealthy in boom is based on our definition. It means that more than 20% of them exceed the unsafe level, but you're not alone. Red is not good, green is good, and you can see that literally the entire eastern United States and other parts of the United States are red, which means that the levels of small particulates are approaching unsafe. And you can read about the health implications. And let's take a look at the one toxic element that exists in boom that is not safe, and it's cadmium. And turns out that about 70% of the measurements for cadmium in the region surrounding boom, which in the case of western North Carolina is about 5 to 10 stations, are unhealthy. But you're not alone. Not that that makes it good. Again, these are the United States. So small particulates and cadmium levels are high. Why is cadmium important? It has a lot of health implications. One of them is airborne cadmium is directly related. It is not the only cause, but it is one of the causes of autism in infants. So it becomes very important to understand what one's air quality is. You live in quite a good place, particularly because you're up high and you get a lot of cold air. So the next thing I was involved in was running a very large program called Greenland Ice Sheet Project 2. After spending a lot of time traversing Greenland, we found a site where the ice was particularly thick, where we thought it would be very old, and between 1989 and 95, spent about close to 30 months in the field, going back through time by drilling 110,000 years, year by year. The longest continuous record of climate ever produced in the world, much less the northern hemisphere. And it actually changed the way we think about climate. And here's the quick reason that it did that. Just focus on this one box on the top. This goes from 0 to 120,000 years ago. And this was the view of climate globally prior to 1992. And that view was temperatures dropped after the last mild period, interglacial, fluctuated a little bit, and then there was the decay of ice sheets, which had gotten quite thick. When we live in Maine, they were at least 1,500 feet thick. And then you go into this what looks like a rather dull flat period, which is the last 11,500 years when civilization emerges. This is what people thought the climate looked like, and this is a very important statement. Because if the climate actually changes this slowly, it doesn't really matter what you do to the atmosphere. You put as many greenhouse gases in the atmosphere as you wanted, because it probably wouldn't respond. However, because you've been looking down, you can see that in fact the climate can change much more rapidly. These are shifts in temperature up and down, and these are shifts in dust related to atmospheric circulation. These are abrupt climate change events, because if you look at the onset or decay of any of these events, these shifts occur in less than 1 to 2 years. They can be sustained for decades, if not centuries, and they are massive shifts in the frequency of storms, the amount of precipitation. In some cases, the temperature shifts are on the order of 15 degrees centigrade, occurring within 2 years and sustaining that way. So our ancient ancestors, it's good that they knew how to run and that they knew how to migrate, because they wouldn't have lasted with some of these shifts. What are these things? We eventually realized that they are related to the position of the jet stream. This is the summer position of the jet stream. This is the air that basically divides the cold air to the north, warm air from the south. And this is the winter position of the jet stream. And these are fast snaps back and forth, such that, for example, the winter situation, which today persists for 3 or 4 months, may have during the particularly cold times persisted for 9. It's a change in the length of the season. If we look at these records a bit more carefully, we see that the most dramatic of these events actually occurred during the glacial period, when the ice masses in the northern hemisphere were very large. And then when you begin to see much smaller variability events, these are times similar to today, when the ice sheets in the Arctic Ocean had configuration of ice more similar to today. You look at this thing and you think to yourself, these are tiny, tiny changes in temperature on the order of tenths of a degree, maybe 1 to 2 degrees centigrade. How important could they be? Well, they can be very important because they're related to shifts in atmospheric circulation, which actually transport that heat. And if you go back from today about 10,000 years, again, this is the time that civilization emerged. These events are much more dampened. You see major events like the collapse of the Mesopotamian Empire 4,200 years ago, a dramatic shift in atmospheric circulation systems, which the temperature wasn't important because this is the Middle East. What was important is the air masses that brought precipitation into these well-developed civilizations suddenly disappeared and the civilization died. Same for the Mayan culture, and quite the opposite around 1000 AD when the Icelanders first went to Greenland. They established cathedrals, they had pastures for sheep, and then by AD 1400 they disappeared completely because it was a fast cooling and they were locked in by sea ice. So even small changes in temperature translated, they changed the distribution, the pattern of atmospheric circulation patterns. I'll show you why in a couple of minutes, can be very important, particularly with respect to precipitation. We see that right now in California and a variety of places. So with this very detailed record, we were able to answer questions: why does climate change? What causes these fast changes? And could human activity actually trigger one of these things? So these cartoons represent all of the basic things that control the climate system. Without going into a lot of detail, we actually see how they vary over time. This one operates very slowly. This is the relationship between the Earth and the Sun, going about tens of thousands of years for change. This one is greenhouse gases, which tends to go up and down with temperature. This one is ocean circulation, which transports heat through the ocean. This one is ice dynamics, which actually in certain situations can allow large discharges of icebergs out into the ocean, which change the color of the ocean, more reflecting or not more radiation. This one is solar variability, which I personally, and actually a lot of modelers, believe impacts Earth's climate through changes in ozone production. And then, of course, things like dusts, naturally from aridification, and of course volcanoes. So you put all these things together, and that's what changes climate. And that never changes. These factors are always changing climate. The question is, which one of these have we had an impact on, and which ones of these can actually cause abrupt climate change? And the answer to which ones can cause abrupt climate change are all of the ones with the stars. Sometimes they come together at just the right time, and sometimes alone they can actually produce something. And it turns out that the ones that humans can actually impact are exactly the same ones. We've impacted greenhouse gases. By adding fresh water from melting of Greenland, we can actually change ocean circulation. By melting ice shelves and creating more icebergs, we've affected ice dynamics. We don't change the energy output of the sun, but we've certainly played around with ozone in the upper atmosphere. We actually, because of urbanization and a variety of other things, can change dust. And while we do not produce volcanoes, we certainly put a lot of sulfur into the atmosphere from acid rain. So we can, in fact, trigger the same things that cause abrupt climate change. Have we done it or not? This is a plot of greenhouse gases going back 800,000 years from the Antarctic ice core record. We did not produce this data, but you can see that the natural range of variability is in about here. 2013, we had already shifted to 1.4 times the natural levels of the last 800,000 years. That's a projection for 2100. But I'll suggest that one of the most important things is the fact that the rise in greenhouse gases is not only 1.4 times more than natural levels, but it's 100 times faster than it has ever been before. So all of a sudden, greenhouse gas is a natural mechanism by which the Earth regulates its temperature. Suddenly, it's as if you put it on speed and make it become even more effective. And the other thing that's lurking in the shadows is methane, which is about 30 times more capable of trapping heat than CO2. It doesn't stay in the atmosphere anywhere near as long, but one of the primary sources of methane, of course, is permafrost, trapped carbon, and as you begin to melt the Arctic, the methane is being released. You've probably all seen this. You go to the Arctic in the winter, dig just above land, and throw a match in, and you actually, there's enough methane coming out that you can actually inflate, you can ignite it. So, next thing to do is continuing in Antarctica, but to go back to Antarctica and all the things that we have learned from GIST, we wanted to see these would work in Antarctica. So I organized 21 countries together. My wife is an artist, and she drew a little sketch of what our traverse would look like. It turned out to look exactly the way it looked in the original cartoon. And we made our way thousands and thousands of kilometers along with our international colleagues around Antarctica. In the process, we collected ice cores, we did snow pits, we did radar profiles to look at how thick the ice is, see how high the ice is versus other time periods using GPS. We put out stations, as do Baker and his colleagues, to take a look at how the weather is changing, the snow levels, and we did atmospheric sampling. And one of the things we found, without going into a lot of detail, we did not do this exclusively, it was many other disciplines, we found that the so-called sleeping giants of the planet, the Greenland ice sheet and the significantly larger Antarctic ice sheet, were in fact changing much faster than we thought. So what we thought when I went from my first expedition to Antarctica, that Antarctica was unchanging in Greenland, and Greenland was absolutely untrue. Things are changing much faster. So we made our way back into the low to mid latitudes to begin to see what is the effect outside of the polar regions. On this particular trip, we rented a little boat in Tierra del Fuego. We made our way into the polar Darwin. Actually, Darwin is right there. Landed by helicopter was simply too steep to get all gear up. Within the first few hours, we tried to do some work. Bang! All of a sudden, the winds picked up to about 100 knots. We spent the next 17 days trapped in our tents, trying to keep from being buried, until we fortuitously managed to get out with a helicopter that crashed into our site and made our way out. We've also been working in the Chilean Andes, far to the south of where Baker, Anton, and his team work, and about the same elevations that we'll be going together in July. And a lot of these regions the ice is just sublimating, it's basically drying away. But if you go high enough, in this particular case, into the crater of a moderately extinct volcano, Mario was here too, we drilled a core and were able to recover a record. And now we've teamed up with Appalachian State because we can provide ice core information, but what you guys do extremely well is to take a look at modern observations and see how temperature, air chemistry, precipitation change so we can calibrate our records probably better than anybody has ever been able to do anywhere else in the world. It's also taken us to Mount Everest, where we've worked up pretty close to 25,000 feet, collecting ice cores several times. These are our Chinese colleagues. I'm going to go visit Chang Kong in a couple of weeks in China. He now has his own institute there. And most recently, one of the most exciting things we've done, Mario and Charles were on this trip. We have rented berths. It takes about 8 people. It's a 74-foot sailboat. And we've sailed from basically the Falkland Islands, not too far from the tip of South America, right out to South Georgia, and made our way in exactly the same inlet that Shackleton landed a little bit more than 100 years ago, and then did the traverse that Shackleton did, and along the way collected ice cores. So this is what it looks like to be traversing along the Shackleton Traverse in South Georgia. Again, you always have to have a good storm and everything. So now let's put this in a little bit more perspective. Yep. Okay, we might actually. So putting this whole thing in modern climate perspective. This is the NOAA reconstruction, phenomenal reconstruction of global land and ocean temperatures for the year, January to December. It's very clear that we're in a period of warming, quite significant, at least a degree centigrade globally. This period of variability in here and a much cooler period. Turns out that this period of variability in here is a time when there was still a lot of sulfur in the atmosphere. And this point right here, where we really begin to see warming, is the advent of the Clean Air Act. A phenomenal legislative success, but it was hiding the other thing that we were doing, which was adding greenhouse gases. It was offsetting greenhouse gases for a while. And but let's take a look at this warming period in here, and let's compare the early warming period from about 1979 to about 1999, and then the time period since then to the present. And the way you do that, Sean Burkle is here. He's a faculty colleague in our institute, and he has developed this remarkable software system that you can get it on a smartphone too. It's called Climate Reanalyzer. And you can look at modern climate, past climate, a whole variety of things. It's an absolutely remarkable tool. And what it allows us to do, you can be standing in a pub and pull this out and show it to people if you choose to. You can actually tell how temperatures are differ between, for example, the last roughly 15 years and the previous 15 or 20 years. And we see that global warming, although it is a great soundbite, we're on our way, but we're not there yet. The warming is not equally distributed around the planet. It's primarily in places where you have ice, and primarily in places where you have thin ice. There are certainly parts of Antarctica that are warming very fast. Notice this red is approaching 2 degrees centigrade. It's a big jump in temperature on an annual basis, and some of the warmest temperatures are in this area up here in the Arctic. And so we'll focus exactly in this in the north first, and let's take a look at what happens to air masses when you change temperatures. This is a schematic of the side of the Earth. Arctic warming quite dramatically, a little less warming down here. The net result is the temperature gradient from the poles to the mid-latitudes flattens out, and as a consequence, this jet stream that divides the cold air from the warm air begins to weaken. The net result is you get more air masses going back and forth. The barrier has been weakened, and therefore you can get more warm air going north, cold air going south. And if you take a look at the wind patterns, what you find, this blue tells you that the winds that run from west to east up in this area are actually weakening at that time. Demonstration that the barrier is weakening. And if you take our ice core records, for example, from throughout Asia, several of these are ice cores, look at the last 50 to 100 years, you see that except for one site, in every single place, the values that tell us how strong the winds were are actually going down while the temperatures are going up. So this provides us, in the case of Asia, a perspective that goes back approximately 50 years, demonstrating what's going on. If we take a look at the southern hemisphere, notice something very interesting. Warming impacts the coastal portions of Antarctica, but the Southern Ocean actually is blue. That's telling you that temperatures in the Southern Ocean are cooling. How did you cool the Southern Ocean in a climate that's warming? Well, the way you do that is partially related to greenhouse gas warming. It's also related to ozone depletion. And as you begin to deplete ozone over the top of Antarctica, which is very high, average elevation 8,000 feet, what you're actually doing is removing heat from the top. The net result is you get a tiny bit of cooling up here, and as a consequence, what you're doing is actually making the Antarctic a tiny bit colder in the inlet, while you're warming the mid-latitudes. The net result is you're strengthening the temperature gradient, so this becomes a stronger barrier, and the winds that go back and forth across this area become weakened. So the initial result of ozone depletion is actually to temporarily protect Antarctica from melting and to protect Antarctica from having much snow enter it, which is important because as sea level rises, it was expected that there would be more precipitation coming onto Antarctica. There isn't necessarily to offset it. And if you take a look at the wind patterns, you see that the winds are actually increasing around Antarctica on the order of about, I'll go back here, on the order of, they're migrating southward, and they're increasing in speed by about 15%, and that's actually pushing cold water up along both coasts of South America. And to get perspective, we have records from our ice cores that go back 10,000 years. It was a moderate warm period in the early part of the Holocene, but relative to the last 5,200 years, this increase in the speed of the westerlies around Antarctica is actually quite anomalous. So let's now see, is there anything about the recent Arctic warming that has relevance to what I talked about? Here is sea ice 1990, sea ice today, and if you translate this using Sean Burkle's climate reanalyzer, and look at the recent time period versus a time period going back to 1979, look at the actual temperatures, you see that in the eastern Arctic, temperatures have risen 8 degrees Fahrenheit. This is annual, 8 degrees Fahrenheit in 5 years. And if you translate that into basically the length of the summer, it's the equivalent of doubling the length of the summer. Imagine if the summer were double where you live, or if the winter were double. So this is truly an abrupt climate change event. It is actually the first very serious indication of an abrupt climate change event, a way in which the climate will eventually change, not just linearly, but it could very well go through these jumps. And as we go back through our record, without going into a lot of detail, this is equivalent in magnitude and speed of change, not necessarily areal extent, but magnitude and speed of change to to the transition between the last vestiges of the Ice Age and modern climate. So this is a big, big, vast event. And it also tells us that if we understand where the jet stream is through time, we were able to explain some of these anomalous features that occurred in the northern hemisphere, and the same in the southern hemisphere. As the westerlies pull southward, they've left Australia and South Africa in drought. I'm sure everybody knows that, whatever, I think 40 days from now, Cape Town, South Africa will run out of water, and it's a consequence of circulation. And if you take a look at some of the very anomalous patterns in atmospheric circulation that are occurring, here's one example again from Sean Burkle's Climate Analyzer. Here's the jet stream, and actually this particular event, close to Christmas Day, tucked its way all the way up into the North Pole, allowing warm air to make its way to the North Pole. So in the middle of winter, completely dark, the temperature at the North Pole was just above freezing. That's how anomalous some of these situations have gone. Here are the big takeaways. Human impact on the chemical and physical climate system is absolutely undeniable. Right? Given talks all over the world, not one climate denier has ever suggested this is not correct. Climate change can be abrupt. Don't assume that what you see today is what will be around in the next few years. Arctic warming is the first example. It creates instabilities in the northern hemisphere, and ozone depletion and greenhouse gases together between the two hemispheres cause these great instability. What are the impacts? I've actually talked about health already with respect to chemistry and warming. I haven't talked about the economy, but you know that. The impact with respect to catastrophes is more extreme events, because there's more exchange of warm and cold air in the northern hemisphere. And when you begin to think about geopolitics, as it turns out, the collapse of the Mesopotamian Empire 4,200 years ago is exactly where modern-day Syria is today. And many people, including me, believe that the Arab Spring was underlain by drought. The farmers could no longer farm, so they began to turn to other things and activism in order to change their situation. But we also have something else happen. We, for the first time in probably at least 200,000 years, if not much, much longer, we have a new ocean appearing on the planet as the Arctic sea ice begins to melt, exposing the Arctic Ocean. The expectation for climate refugees in the future, next few decades, is on the order of 100 million. That's within the range of 60 million, the climate refugees that are being displaced in the Middle East right now. So, T.S. Eliot said it much better than I could. It turns out that sometimes you have to go far away from home to understand what's going on at home. Thanks so much for listening.
Thank you, Paul, and we do have some time for some questions here. So if anybody has a question, you can raise your hand and Paul.
And if you need to leave, please do. I won't be insulted. So, any questions? Yes?
How well did your ice cores in Greenland pick up the Younger Dryas?
That's an excellent question. How well do our ice cores pick up the Younger Dryas? The Younger Dryas is, after the major ice sheets begin to decay, a few hundred years after that, there's a slight return to the expansion of northern hemisphere ice sheets and other ice masses in other parts of the world. It's considered to be one of the most important abrupt climate change events that we look at. And in fact, the reason that we know the abrupt climate change events occur in 1 to 2 years is because as we went through this Greenland record, when we went obviously from younger to older, as soon as we went into the Younger Dryas, that's when we first saw that giant jump. Not only do you see the jump into the Younger Dryas in and out in about 2 years, but you can actually see a precursor of it. The system tries to go into it before that, and you can see within the Younger Dryas these three classic, particularly cold periods in the Younger Dryas. And nowadays, with this new laser technology that we've developed, we're getting on the order of about 500 samples per year during the Younger Dryas and 1,500 samples per year at the onset of the Holocene. So that's the equivalent. We're not saying that each one of those represents a day, but it clearly is the equivalent of storm sampling. And we can actually, it's from that Younger Dryas that we've transition from the young dry ice into the Holocene, when in fact the length of the summer doubles. That's where our estimate for basically a more expansive version of the modern abrupt Arctic warming comes. So thank you for that question. Yes.
The particulate that we get here in Boone, is that still coming from Ohio River Valley Midwest production, or is it fires, or where is that coming from?
It's probably coming from all of those things. It's primarily coming from areas to the west of you, obviously. And it's interesting, in Maine, I don't know enough about North Carolina to judge, but I don't think you're a big industrial state. Maine is definitely not an industrial state, and all of the pollution that we get comes from Canada and from the west. And even under a relatively environmentally minded, well, I shouldn't say that, even under different administrations, it turns out that there was legislation that was passed that said that every state has to clean up its air quality, and Maine was told we need to clean up our air quality. We said, well, that's fine, except that dirt doesn't come from us. Similar to your city, particularly here in western North Carolina, it's definitely not coming from North Carolina. So, but these are all things. Granted, it's not trivial to reduce particulates in the atmosphere or cadmium, but it's extremely important. And studies that have been done, for example, interestingly enough, by the oil industry to offset interest in the coal industry, they took a look at the frequency of disease and the rate of death of people in various circles surrounding coal-fired plants. And because one of the biggest problems with telling how much people are impacted by something has to do with all of the things that make us who we are, and it's very hard to say that this happens to all people, but this is a very simple exercise because it doesn't matter what your gender, what your race, what it is. If you just take a look at how many people die compared to other areas, depending on how close you are to a coal-fired plant, you find that the levels are significantly higher. So living close to these pollution sources is definitely not good. And one of the reasons that we produced this 10 green, this simple number that you could drill down into, was to energize people. They look at it, and let's say you're thinking, should I live in western North Carolina or should I live in Los Angeles? The two jobs are exactly equivalent, and if I care about air quality and my health, I would choose western North Carolina. It has significantly cleaner air, and that's not a trivial thing to decide.
All right, okay, one more question here.
So, based off of your research and what you found, what do you think is done as far as legislation? Do you think no action needs to be taken right now? We focus on one thing or another?
I didn't put it in this overhead, but I would make a point, and in fact, the Pentagon makes the same point, that climate change is one of the most important security issues of the 21st century. And the Pentagon goes almost as far as I do to say that abrupt climate change is extremely important too. So, one way of thinking about this is, okay, fine, we have a lot of important security issues. Maybe climate change is one of them, but there are other things that are more important. Bottom line is, this is a big country. We need to be looking at a variety of things at the same time. And what are the solutions? The solutions, you know what some of the basic solutions are that have to do with emissions from your vehicles, how much heat you use, how clean the water is, all of those things. But what we're trying to do, particularly with Sean's climate analyzer, is to put together a new way of looking at the climate systems called Climate Futures. And it's actually a platform that takes Climate Reanalyzer and other software and allows you to understand where you are in the climate system. Have you experienced warming? Have you experienced drought? What are the conditions under which that happens? So that you can project a little bit more easily into the near future, which is critically important. And it also allows you to take, for example, a commodity. In the case of Maine, potatoes are a big deal. Forestry is a big deal. Lobster is a big deal. And it turns out that Maine potatoes are about 40 to 60% directly related to what the climate system is doing. Some of it's economic, variety of other things. And so now, using this framework, once it's completed, you will be able to interactively interject a time series for potato production and see how it will change by X amount of temperature and precipitation change based on the record going back 50, 60 years, and therefore make better projections about what type of potato or whether or not you should even be growing potatoes in the future. And this is not just something simple like temperature changes, potatoes change. It also we were able to see how the circulation patterns change. And then this framework called Climate Futures goes further than that. It not only allows you to get a background of climate, it allows you to take a look and see what the models project versus what we learned from a modern time period. And it also develops allows you to develop what are called plausible scenarios for the future. One way of looking at the future of climate is to say by 2100 the temperature will rise 3 to 4 degrees centigrade. And fine. Many people in this room will be around in 2100, and that's important, but you wouldn't necessarily assume that it will impact your life. But plausible scenario planning is not just one trajectory, it's a situation used by the military and by businesses to come up with 4 or 5 different projections for how the climate might occur. What's the value of that? You get everybody into the room who cares about this. Everybody, people who believe nothing will change, people like me who think things can change very, very fast. You sort of project yourself to the year 2020 or 2030, and with the knowledge of your local area, knowing where the vulnerabilities are in terms of climate response to agriculture, icing of roads, etc., and what your assets are, a lot of water, not enough water, you can then begin to make these 4 projections of climate in the near future. And of course, the best solution is the one that's going to deal with addressing the vulnerabilities for as many plausible scenarios as you can. And then as time goes on, not too long, 1 or 2 or 3 years, you'll begin to see that maybe one of these plausible scenarios isn't so plausible anymore. It's a way of educating people, it's a way of getting people to think about climate, and there are parts of the world where the answer is not good. If you live in a South Pacific island, the plausible scenario is, as many countries, South Pacific Islanders are, is better buy a land in another country. But for many places, understanding how things will change doesn't necessarily mean that it's the end of the world. In fact, it could be an opportunity. Great example is in the field of agriculture, places like Bangladesh are gradually going underwater, and the crops are dying because there's too much salt. So there are people who have now figured out how do you actually find crops that can deal with people from Bangladesh can't just move that easily. So salt-tolerating crops and a variety of other things. So although this is a very serious story, I think that the possibility for finding a future that is innovative, entrepreneurial, is very, very high. And because things like air quality, not greenhouse gas version, but the other ones can be cleaned up, you could live in an environment which has much cleaner air, therefore you will be healthier. And if you understand what's going, imagine if you understood how the stock market would react in the next few years. I think there's a better chance of understanding how the climate will respond than understanding exactly what will happen in the stock market in the next 10 years. So, education and then great, bright ideas. And these range, these are not just for scientists, these are for engineers, these are for business people, people in policy. Every single field that you're involved in can be impacted by understanding the climate system today and where it will go in the future.
All right, thank you very much, Paul.
Yeah.